good morning, good afternoon, good evening, whenever you are listening. This is Dr. Jenkins. Here we are to start our next chapter, which is all about muscle. So if we think back to where we've been coming from, we did some intro chapters on how to describe motion, kinematics, kinetics, and then we talked about the bones. Then we talked about articulations or joints. And here we are talking about muscles. Muscles, muscles, muscles. In this first video, I'm hoping a lot of it is a review. Like I've said before, if you're not as up to date on these things from anatomy and physiology, then you're going to have to spend time with them again to make sure that you are understanding these concepts, because we're just going to add on to it, all right? Okay, let's see. If you're following along in the notes, let me pick red. I think red will be good. You can see up top there, Roman numeral number 1, characteristics of muscle tissue. I want to point out two characteristics. That is that muscle tissue has contractility, which means it is contractile. All that means, folks, is that it can contract. How about that? I know this might seem kind of silly to point out, but this is a function of this specific tissue, muscle tissue. Not every tissue can do it. If I send a nerve impulse stimulus to your skin, it can't contract, right? So muscle tissue is set up in a certain way, which allows it to be contractile. So it's a unique characteristic of muscle tissue. It is true of cardiac, skeletal, and all types of muscle tissue, cardiac, skeletal, and smooth. Another characteristic I want to point out about this muscle tissue is that it has elasticity, which means it is elastic. What we're saying, folks, is after it contracts, muscle tissue can return to its original position. So it's elastic. After contraction, muscle tissue is built to return to its original position or structure. Again, not all tissue is elastic in this way. Typically, every tissue in the body has some elasticity, but often not very much. Muscle tissue has a lot of it. These are the characteristics that allow muscle to do what it does for us. It can forcefully contract to create movement and propel things. And after it contracts, it can return to its original position, which means that we can come back to it again and again. So it can continue to contract for us and return to its original position. There are 3 different types of muscle. So there are skeletal, there's skeletal muscle, there's cardiac muscle, and then there's smooth muscle. 3 types of muscle tissue in the body. Of course, we're going to be focusing most on skeletal. Skeletal muscle is the muscle attached to bone. When you think of a muscle, you're probably thinking of the skeletal muscle. Biceps brachii, triceps brachii, hamstrings, quads, trapezius, latissimus dorsi, rectus abdominis, and so forth. This is what skeletal muscle looks like under a microscope. I'm hoping you've seen this before, folks. I'm going to point out some important characteristics right out of your notes. If you look at skeletal muscle tissue, it's striated. Vertically, when you look at this vertically, you can almost see white vertical striations, white lines like zebra stripes. That's a very important structural characteristic. Skeletal muscle tissue is multinucleate. I don't need to say what that means, do I? Has many nuclei. That's important. And unlike both of the other muscle tissues, skeletal muscle is the only muscle tissue that is voluntarily controlled. You voluntarily decide when you're going to contract your biceps brachii. Not true for your cardiac muscle. That occurs involuntarily. Good. Okay, we are going to do a review of the skeletal muscle. So from here on out, folks, We are talking about skeletal muscle, not cardiac, not smooth, skeletal muscle. And by the way, this is the type of muscle tissue we have the most of. I want to say we have over 600 skeletal muscles attached to bone that help us move. They're everywhere. Make sure you review the basic structure of a skeletal muscle. You will need to know these. Should be a review. So as I was saying, if it's coming back to you, great, review, make sure you got it. If it is not coming back to you, you absolutely need to spend time. A lot of this is memorization. I know the words sound similar and whatever, but with time, repetition over and over again, you can absolutely memorize these. So let's look at the whole muscle, right? So this could be, this round thing here could be any muscle, biceps brachii, gastrocnemius, whatever. The entire skeletal muscle is made up of these bundles called fascicles. So each one of these is a fascicle. That's a fascicle, this is a fascicle. So the entire skeletal muscle is made up of these bundles called fascicles. Excuse me. I knew that was coming. I think I have another one coming. I apologize. Pardon me. So each fascicle then, if we look at each fascicle is made up of these individual muscle fibers. Actually, I'll change color. Maybe that will help. Maybe I'll make the fascicles green. How about that? So each individual bundle that makes up the fascicle is called the muscle fiber. So here we've pulled out just one muscle fiber. If you hear muscle cell, it's basically analogous to a muscle fiber. Excuse me, I have to blow my nose and I really apologize. Okay, my apologies. And then each muscle fiber is made up of smaller components called myofibrils. And each myofibril is made up of the smallest components of muscle, which are myofilaments. These are the smallest. These, folks, are the pieces that are contractile. So it is the myofilaments that are able to slide past each other to create contraction. Excuse me. Good. So these are the contractile. You should be reviewing what I'm talking about. You also want to review the different types of myofilaments. Actin is the thin myofilament here in yellow, and myosin is the thick myofilament here in red. Okay. If we look at your notes, we're going to talk more about the muscle fibers, and I'm going to open up another page here so we can take some notes. So a lot of times we're focusing our discussion in this class on the muscle fiber or the muscle cell. As you can see on your notes, there are different types of muscle fibers. There are different types of muscle fibers. So once we know what a muscle fiber is, let's talk about the different types. And I hope you've heard about these before, folks. There's type 1 muscle fiber. These are the slow twitch. These are the oxidative. What does oxidative mean? Requires oxygen. Type 1, slow twitch, oxidative. These are the muscle fibers that are slow to contract, but stay contracted for a long period of time. So they're slow to actually contract, but stay contracted for longer. They're also at a slightly lower intensity than the type 2. They're not as strong, but the benefit of these is that they can stay contracted for longer. Then we have our type 2. I'll change color, keep things interesting. Let's go for a darker green. Yes. Then we have type 2. Overall, the type 2 would be the fast twitch. And whatever we said about the slow twitch, the fast twitch is usually the reverse. But we're going to be more specific. We have type 2A and type 2B. As it says on your notes, type 2A are the fast twitch oxidative, requires oxygen. Type 2B are the non-oxidative or anaerobic. They do not require oxygen. There I was saying anaerobic and I wrote an A. Non-oxidative, do not require oxygen. Yes. In general, the fast twitch are quicker to contract, but the quickest to contract is the type 2B. Quickest to contract. The ones that can fire at the highest intensity would be the type 2B. These stay contracted for the shortest period of time. Contract for shortest duration. Okay. The oxidative will lie somewhere in the middle. Not as slow to contract as the slow twitch type 1, but not as slow as the type 1 slow twitch, but certainly faster, but not as fast as the 2B. What I want to point out is every muscle has both. Let's go for a picture here. Yeah, well, there's another picture of just the structure. Here's more information about the type 1 and then the type 2A, type 2B. Every muscle fiber has both. So in this picture, this is an actual, it's like we went into the muscle and took a biopsy. We shoved a needle in there. Actually, if you want to know the truth of it, to get a muscle biopsy, it's almost like a soil sampler where you plunge it's thicker than a needle really, or it's a huge ass needle. You plunge a big needle into the skin through the muscle, and then you take out a sample from the center, like a soil sample. So if we look at a muscle fiber sample under the microscope, we can stain it such that we can see the different types. Okay? So the slow twitch here stained the darkest. So we have some slow twitch, but then we have some fast twitch oxidative, which would be type 2B. They stain this lighter purple. And then we have fast twitch, I had that backwards. Fast twitch oxidative are the light purple. I think I just make sure I say that properly. And then the fast twitch glycolytic, which are the fastest to contract, are these lighter ones. So every muscle has all three. It is not like every muscle has just type 1 or just type 2A. Every muscle has all three. However, we can have different compositions of them. Let me see if I have... Okay. Sorry for the going back and forth. I just want to make sure I see what I'm talking about here. So every muscle has some of all three, but we can give examples where there's more of one or the other. A postural muscle, like your rectus abdominis. A postural muscle is going to have more type 1 muscle fibers because it's going to contract at a slightly lower intensity but stay contracted for longer to help you maintain your posture and stand upright. Let's take, on the other hand, something like your biceps brachii. That usually tends to have a higher amount of type 2 muscle fibers because it doesn't need to contract for long periods to hold you up or anything, but your biceps brachii is meant to contract at really high intensity for shorter periods of time. So every muscle has all three, But, certain muscles can have more of one versus the other. I'm going to add some information here that is extra, so you don't need to know it. If you wanted to get an idea, again, you don't need to know this. On an average basis, around 50% of all of our muscle fibers are type 1. You don't need to know this, just giving you examples. On average, about 25 to 30% of all of our muscle fibers are type 2B, which means that the lowest number that we have would be type 2B, somewhere around 15%. You don't need to know those, but that's usually somewhat the breakdown. Let's review what I would like you to know. Let's get a new page here. I try and be very clear, folks, right? So the benefit of taking the time to listen to this and take good notes, I mean, that's really the least I'm asking you to do is just listen and take the notes. You really got to study, obviously. But the benefit of taking your time with this is that you know exactly what to study and then exactly what you don't need to know. All right. So what to know about muscle fibers? I would like you to know that we have the least amount of type 2B. I'm not going to ask you the specific percentage, but you should know that we have the least amount of type 2B. Did I make sure? Yeah. Okay. The type 2B are the quickest to be lost over time. We lose type 2B fastest with age. And I bring this up because we see this, folks. I mean, if I just ask you this, you probably already know it. I'm just providing the physiological rationale that explains it. So if we think about the fastest sprinters in the world, and that's why I have these examples. Well, one reason why I have them. Usain Bolt at one point had the 9.58 100-meter sprint record. He would be using mostly type 2 muscle fibers for such a short distance. He's going to be using a lot of type 2B. On the other hand, a marathon runner, there is a newer marathon record, of course, since here, but a marathon runner is going to be utilizing more of type 1 muscle fibers. Wouldn't the type 1 or slow twitch muscle fibers be more geared for a marathon? Slower to contract, but can stay contracted for longer. So I would like you to know that, for example, a marathon runner is going to be utilizing more type 1 muscle fibers versus a sprinter is going to be utilizing more type 2, particularly 2B. Remember, even though we have both, our muscles have all of them, based on your area of training, you might be training more of one versus the other. I don't think that's surprising. But let's take it to where I was going before. What is the age? What is the usual age of Olympic champion sprinters? What is the age of Olympic champion sprinters? Probably they peak in their mid-20s. They probably peak in mid-20s. I'm not going to ask you that, but I'm just making a point. What about the world-class marathoners? They actually tend to peak in their 30s. Why? You will see older people win marathons. You will not see, it's very unlikely that you'll see a 35-year-old win the 100-meter sprint at the Olympics. What is one of the reasons behind this? Probably the primary reason is that as we age, the first type of muscle fiber that we lose is the type 2B. We lose type 2B the fastest. This is the rationale explaining why the fastest sprinters in the world are younger compared to the fastest marathoners and when they can peak. It is possible to change some of these over time. We can convert to a certain degree one fiber type to the other, but I don't think it's as much as we once thought. So training will definitely help you develop more of one muscle fiber type versus the other. However, the ability to convert muscle fibers from one type to the other is not as common, doesn't happen as much as we once thought. Other goodies in the PowerPoint, years ago, many years ago, now that I'm aging myself, I read a book called Taboo. And the reason, it's 2001, so it's been around for quite a while. When it came out, this book was kind of condemned by some people. And the reason why the author labeled it taboo is because he knew that was going to happen. Some people believe it's taboo to talk about this topic. As a scientist, I have no problem talking about some objective data, right? We're not making any judgments. It's just objective data. This is extra. Not going to be on the test, but did you know Black and African American athletes have higher numbers of type 2 muscle fibers compared to people who are Caucasian? It's a fact insofar as we've taken muscle biopsies from thousands of athletes, and these are the results that we've gotten for those thousands of athletes. I think we see this play out. I mean, if we think about the sprinters, a lot of the fastest sprinters in the world are of African descent. They are helped, perhaps, by the fact that they've got a greater number of type 2 muscle fibers. Think about the NFL. People, this is a fun question to ask. Who is usually well, I guess if you're a football player, you know this, but if you're just a fan, you might not. Who is usually the person who is fastest on the field? Not the wide receiver, but the cornerback. The cornerback has to react to the wide receiver, and therefore, being a split second faster will benefit the cornerback. Think about the top tier cornerbacks, even running backs, folks. Top tier wide receivers. These are all sporting positions that require a lot of type 2 muscle fibers. And therefore, we tend to see a lot more African American. There are other factors that play a role, of course. The book Taboo tried to think about what are some reasons in evolutionary terms why this might be the case. You don't need to know this, but sometimes it can be interesting. There is such a thing. We know it. African Americans and people of African descent are more likely to have sickle cell anemia. Sickle cell anemia is, I would say, proven to be a trait developed over time as a preventative to malaria. And maybe perhaps one of the other effects of this adaptation as a protective mechanism against malaria is the incidence of a high number of type 2 muscle fibers. You don't need to know these. I'm just telling you. In the book Taboo, the author, John Entine, actually breaks down the best runners in the world. How much of it is due to their muscle fiber composition versus their training, versus their access, versus their level of competition. It's impossible to extract the exact difference, but if we look at the continent of Africa, most of the Western Africans and the Caribbean is also populated by a lot of people of West African descent. So here we tend to see a lot of the fastest sprinters in the world. Here we tend to see a lot of the fastest descendants from the middle distance. And then here we can see more of the distance runners, for example, Kenya. Don't need to know this, but it's just interesting. Okay, if we are looking more at the anatomy review, all right, here we go. Make sure you review the myofibril. The myofibril has the sarcoplasmic reticulum. The sarcoplasmic reticulum is that blue covering over each myofibril. It's kind of like a net or a mesh, that blue-purple covering. The function of the sarcoplasmic reticulum is to store calcium, We need calcium for muscle contraction. This is where it's stored. Make sure you review that. We also already reviewed actin and myosin. Actin is the thin, in this case blue. Myosin is the thick, red. Actin has 2 subunits, troponin and tropomyosin. You don't need to know those. Well, actually, just know that troponin and tropomyosin are subunits on actin. Troponin and tropomyosin are subunits on actin. For me, you don't need to know the sarcomere labeling, so you don't need to know the Z-disc or the H-zone or the I-band. I would rather us put our study efforts towards something else. You don't need to know those. All right. Here's what the actin and myosin look like for real under a microscope. It's not always going to be as pretty as this arrangement. They do this so we can understand what's happening, but in reality, the actin and myosin tend to kind of be a little bit more squished together. Right? We already know that when a muscle contracts, the myofilaments slide past each other. So here on the top is a relaxed sarcomere where the actin and myosin have a space between them. Let's go with it. What color should I use? I'm so indecisive all of a sudden. That's unusual for me. So here we can see a space, right? This space between the actin and myosin is representing, well, more specifically, between the actin, right? Actin ends here, actin, there's a space in between. That's what a relaxed muscle looks like. But those myofilaments will slide past each other. So when they're contracted, they're touching, no longer a space. The epimysium is some people say epimysium, I say epimysium. That's the connective tissue covering over the skeletal muscle. All right, I would like you to review the basics of the sliding filament theory. I have listed the steps for you in your notes. Excuse me again for blowing my nose. I have listed them on your notes. I have listed them here in words, and I've listed them here in a visual form. Let me hit the basics, but I'd like you to review all of them, okay? Let's pick a brighter red. Yeah. So I just want to remind you that in order for a skeletal muscle to contract, it needs a nerve impulse stimulus. The nerve impulse is the stimulus to tell the muscle to contract. We know that that nerve impulse is going to cross the synapse into the muscle over the neuromuscular junction. The neurotransmitter responsible for crossing that synapse is acetylcholine. Once we get that nerve impulse transferred into the muscle, the nerve impulse or action potential, AP means action potential, which is the same thing as a nerve impulse in this case. It's going to travel, that nerve impulse is going to travel down to the sarcoplasmic reticulum, which stores calcium. But now that the nerve impulse has gotten to the SR will release calcium. Calcium will diffuse deeper into the muscle, and it will bind to troponin, which is the subunit on actin. When calcium binds to troponin, troponin will shift to open up the active sites on actin. Only after that happens can we have the cross-bridging. Cross-bridging is when the myosin head perks up and attaches to the active site on actin. No movement yet other than the myosin head attaching to actin. And then, of course, the actual contraction is called the power stroke, when the myosin head releases its stored energy and it kind of pivots, the myosin pivots, causing actin and myosin to slide together. However, as quickly as it slides together, it is removed because a new ATP comes over and pulls the myosin head off of actin. However, as long as there are continually nerve impulses coming into the muscle, this cycle will repeat. Review, review, review. Make sure you can define motor unit. Make sure you can define motor unit. A motor unit, I didn't get the definition, did I? No. A motor unit is one nerve, one motor neuron, and all the muscle fibers that nerve innervates or supplies. A motor unit is one nerve and all the muscle fibers it supplies. A motor unit is one nerve and all the muscle fibers it supplies or innervates. I like this picture on the left because it's simple. Look, the red is motor unit number 2. Look at the red. We have a motor neuron. How many muscle fibers are supplied by that red motor unit? It goes here, that's 1. It goes to this muscle fiber, that's 2. And it goes over here, that's 3. So collectively, that motor unit number 2, collectively, it is the red nerve and the 3 muscle fibers it supplies. What about the purple one? What about the purple one? The purple motor unit is the purple nerve and however many muscle fibers it supplies. The purple one supplies this one here and then this one down here. So the purple motor unit is the purple nerve and the 2 muscle fibers it supplies. On the right is a picture of what it really looks like, of that motor neuron coming down with little tendrils wrapping around the muscle fibers. Please make sure you review the laws of the motor unit. If a nerve impulse goes down a motor unit, either all of the muscle fibers it supplies contract or none contract at all. Within a motor unit, if a nerve impulse goes down it, either all the muscle fibers contract or none contract at all. So for example, in motor unit number 2, it was 1 motor nerve and then the 3 muscle fibers innervates. If we send a nerve impulse down motor unit number 2, either all 3 of those muscle fibers contract or none contract at all. You can't contract one muscle fiber but not the others. Each individual contraction is the same intensity. How then do we determine the overall intensity of a muscle contraction? The number of motor units activated. If each muscle fiber is the same intensity of contraction, how do I alter the overall contraction? Strength of a muscle is by contracting more or less of them. Each individual one is the same, but I can contract more overall, or I can contract less overall. Good, good, good. Listen, folks, different muscles have different size motor units. Be able to give an example of maybe an area or a muscle where we'd have a small motor unit versus an area or a muscle with a large motor unit. For a small motor unit, like these pictures here, small motor unit. Let's say we have 1 nerve supplying 3 muscle fibers. That's a pretty small motor unit. What type of muscle would benefit from this arrangement? Small muscles of the hands or face. So an example where we might see small motor units would be muscles of the hand. Because in the muscles of the hand, it's usually not overall force that is our biggest concern. Usually with muscles of the hand, for example, we want to have more intricate, complex movement. So I have many, many small muscles with small motor units, and I can contract this one, but not that one. And because of that, I don't have great force overall, but I have a lot of control. I can play the piano. Imagine how many small motor units that takes to contract some muscles, but not others, to move your fingers and hands in all sorts of ways. On the other hand, an example of a large motor unit might be a big muscle group like your quads. In this case, we might have 1 nerve that supplies 100 muscle fibers or even 200. So an example here would be like the quads, a large muscle group where we don't need as much control. I mean, we contract the quads, it extends the leg. There's not much else to say about it. But here, the benefit is more overall strength. Because with one nerve impulse, with that same one nerve impulse, I can contract 100 muscle fibers. That's crazy. How efficient is that? Right? It's very efficient. I can take that one same nerve impulse, but I can contract 100 muscle fibers. Cool, cool, cool. Last thing on there, recruitment of motor units. When we start physical activity, we start just by nature. Your body will recruit smaller motor units first and then larger. Your body will recruit smaller motor units first and then larger. This, folks, is evidence, one piece of evidence, of why a warm-up is so important for athletes. If you warm up, you're giving your body time to activate the small motor units and then start to get to the big ones where you can generate more force. Okay, I'm looking at my notes here because I want to see what we got going on here. Okay. I'm considering how far I need to get for this first video to make sure that we have time in lecture for the rest. Okay. And looking at the schedule, make sure we're on. Good, we're good. Okay. So the last thing I want to do in this video before we meet again in person is to just review the stages of contraction. If we send one stimulus, if we send one nerve impulse, we'll get one muscle contraction and then it will relax. That's what a twitch is. Think about one singular nerve impulse will result in one cycle of muscle contraction and then relax. We rely on twitches to close our eyeball, help contract the muscles to close our eyeball if there's a speck of dust coming into it. But most of our actions, even if it's just writing, the muscles in our hand used to write, or the muscles in our legs used to help us walk, or a physical activity or sport, most of them require more than a twitch. One nerve impulse and one cycle of contraction gives you a twitch and then you're done. But most of our actions require sustained muscle contraction. When we want to have a sustained contraction, we want to send repeated nerve impulses. And this is what we're going to talk about. So a twitch is only good for one nerve impulse, one little twitch, done. But most of our activities require sustained muscle contraction. We hold that contraction to actually grip a pen or walk or kick a soccer ball or run or whatever. So when we want to have that sustained contraction, we go through these steps. The next thing is summation. We begin to send more nerve impulses more quickly to the muscle. Because, folks, it's not just one nerve impulse that we need for a muscle to contract and stay contracted. One nerve impulse will only give us one contraction, then we're done. So we need to send multiple nerve impulses. In summation, those multiple stimuli that we send, the multiple nerve impulses that we send, build on each other. If we look at this graph, right? If we look at this graph, I know it's simple, but it can tell us a lot. If I send one nerve impulse, muscle contracts and it relaxes. What if I send a second nerve impulse? Muscle will again contract and it will begin to relax. But what if I send a third stimulus before it even had a chance to relax, back to resting? Well, then the effects begin to summate. And you would see the effects going like that. Eventually, we're going to get to something called incomplete tetanus. Incomplete tetanus is like a quivering contraction. Complete tetanus, we send so many nerve impulses so quickly that we sustained contraction. Now, this is happening really quickly. you're not going to feel that quivering contraction because we move through all these so quickly to get to that sustained contraction. But it is happening in really, really small quantities of time. When I think about the quivering or the incomplete tetanus, the easiest example I can think of is that you initially went through all 4 of these to get your sustained contraction. Let's say, this is the last topic, let's say that I was doing a bench press. Okay, folks, I have no upper body strength, right? I do a lot of cycling. It's all in my legs. So if I do some bench presses, I'm going to move through these quickly. Yeah, I got it, right? I'm contracting my pectoralis major and my triceps brachii and all that. But as I get fatigued, even though I'm sending a nerve impulse for my brain to tell the muscle to contract, it may not be able to. There might not be enough energy getting into it. It may not be able to structurally handle it. So if I've already gone through all the stages, but then I tire, you might work backwards. Have you ever worked yourself so hard that your arms begin to quiver? Like really begin to quiver. But what's happening is your muscles can't handle the load any longer, and they will start to revert. So I could actually be on that bench press bench trying to do another rep. Oh my goodness. And I could have quivering muscles, which is an indication that I'm sliding backwards, and I'm probably very close to muscle failure. That's why I need a spotter. All right. We will pick up here when I see you on Thursday. Let's study hard, folks.